Thank you very much for the introduction and for the opportunity to be here. This talk, well, I had to submit the title some time ago, and maybe a more accurate title would be Developments in JT and 3D Gravity, I suppose. So this is a talk that is based off of the papers that were written a long time ago on the basis of this Frontiers of Science Award. And so my paper is up here, Genbin's is down here. Unfortunately, Herman couldn't join us. He was stuck in Princeton. These papers are quite old. These are from 2016, and they are pretty well known in the community. And so in planning this talk, to be honest, I've really been struggling with what to do something that would be satisfying to an audience of friends and also people that maybe are not so familiar with these things. I want to give something for people that know the story very well to satisfy them, and also to say something about the old papers for those that haven't been following these developments. And so at the end of the day, what I decided to do was to give mostly the backstory, sort of a historical retrospective on this paper and my involvement in this. It's interesting to give a talk where you reflect on these sort of factors in this history. I've never given a talk like that in my life before, but it was fun for me. Hopefully it'll be fun for you too. And then at the end, I'll talk a bit about some work that this blossomed into in the context of three-dimensional gravity. Unfortunately, there'll be absolutely nothing new in it. The new things, at least my contributions to them, will cut off 5 years ago, although I'll comment on some developments that people in this room have contributed since then. So it's a very short outline. All right, so for me, where the story began was something a little bit over 10 years ago. It was a long-term program at KITP, and at the time, Alexei Kitaev gave a series of 2 talks, one in April and the second in late May, proposing what we would now call Sachdev-Kitaev models as a toy model for holography, and in particular, holography in 2 dimensions. Now, within a month of his second talk, Subir wrote a paper. This wanted to make sure that everyone remembered that he was really responsible for generating these models in the first place. And so he wrote some paper that, I did something wrong. Okay, sorry. He wrote a paper that was mostly focused, Kitaev's talk, the main basis of his proposal was that SYK models would have some holographic dual on the basis of some fast scrambling, some maximal Lyapunov growth of out-of-time ordered correlators. And the observation that Subir was passing on was of a somewhat different nature, something that was visible in the original Sachdev models, not the SYK ones, models where there's U1 global symmetry and you can turn on the chemical potential and study charge, relaxation, and diffusion and such. And what at the time had been a focus of an enormous amount of attention, namely extremal Reisner-Nordstrom black brains. And in this paper, he notes that there's some relation between the Green's function of fermion, like operators dual to fermions deep in the throat of an ADS-RN black hole at 0 temperature, and a quantity called spectral asymmetry by him. That's what this calligraphic E here is, although I'm not telling you exactly what it is. It's some property of the 2-point function of fermionic operators. And he uncovered some relation between that and low temperature thermodynamics that was shared amongst ADS Reisner-Nordstrom, as well as Sachdev models. And he said, this is some strong evidence for a potential duality. And the reason why this had something to do with me is that at the time, I was a lot younger. This is what I looked like back then, according to the internet. So I was a postdoc at the Yang Institute at Stony Brook, and my postdoctoral supervisor, Chris Herzog, was faculty there at the time, and he got Subir's paper to referee. This is all out there in the open anyway, since we ended up telling Subir at some point that we were the referees for this. So nothing here this is all public information anyway. But what he was trying to do at the time as a good, honest referee was to understand that this relation that Subir was so excited about was merely a consequence of low energy conformal symmetry, like many other things that were shared between holographic theories and strongly correlated ones. And, he was playing with this for some time, and eventually he convinced me to tackle the problem with him and be joint referees of this paper. And he eventually told Subir what we were doing, and then we were dropped as the referees. But okay, so that was one thing that was on the mind at the time. There was another question, though, that at the time it wasn't clear whether it'd be related or not. It ended up being very closely related, which was a long-standing problem concerning the role of ADS2 throats in ADS-CFT. And to set this up, let's remember the usual story, the one that leads to the ADS-CFT correspondence and Juan's original paper, which is that when we have ADS throats with D bigger than 2, that those throats decouple at low energies. That is to say, if you study low energy excitations in the background, that ones that start in the throat, they stay stuck in the throat. It becomes its own self-contained world. And this is one of the crucial insights, of course, underlying ADS-CFT, whereby ADS5 times S5, that becomes its own nice decoupled world and has some dual description. Now, I said ADS bigger than 2. In ADS2, this is demonstrably not the case. This result, I think it was known in some sort of form going back all the way to Wilczek in the early 90s, but the first paper that really spelled this out in detail was the one of Juan and Michelson and Strominger in 99, and the sort of slogan that summarizes a lot of it is that ADS2 doesn't support finite energy excitations. And while this sort of non-decoupling, this was an annoying problem because unlike, D1, D5, where you have a nice ADS3 regime in the deep infrared, there was no nice limit for ADS2, and ADS2 is ubiquitous. It's the universal, nearly universal near extremal geometry in string theory. And so we wouldn't have something really simple like an emergent conformal quantum mechanics describing the microstates of an extremal black hole. And this problem came up from time to time, and in particular, it was on Joe's mind, I think, ever since the paper of Juan and Michelson and Strominger. And it intersected my life in the heyday of applied ADS-CFT, where this problem kind of came up again in the context of extremal ADS Reisner-Nordstrom black brains. So in 2011, I was fortunate to end up having a paper with Joe and my former supervisor and Shamit and Eva, where we were tackling some problem that doesn't matter for this about applied ADS-CFT. And at some point in the development of this manuscript, there was a part of it that just appeared. And I found out shortly thereafter that it was Joe, and this was his something that he just slipped in. And I won't say if it's the biggest part of his contribution or not, but there was some part where he gives an argument using sort of quantum mechanical language, not gravity language, but quantum mechanical language, why if you had conformal symmetry in 0 plus 1, why it would have to break down at low energies. And I would be remiss if I didn't mention that Hong Lu and friends made a similar argument in a paper that appeared right around the same time. And now this argument, I think it's responsible for maybe 80 or 90% of the citations of that paper that it received since then. It wasn't quite right in the details, but it was right in the spirit of it. And at least to my mind, this can be forgiven because at the time there were many confusions swirling in the air about what on earth to do with ADS2. And just to give you an example of some of the things that we don't talk about anymore that were in papers and in discussions at the time, one was that at least, did I do it again? Shoot, okay. Was that formally ADS2 boundaries appear to enjoy an infinite dimensional conformal symmetry. You can do a reparameterization, roughly speaking, any reparameterization in 0 plus 1 can be undone with a Weyl rescaling. And that looks like an infinite dimensional conformal symmetry akin to what one finds in 1 plus 1 dimensional CFT. And so you might wonder, as some authors suggested, if there was a Virasoro symmetry governing ADS2 like there is in ADS3. There was another thing that I think appeared a lot in discussions, maybe less so in print. If you ask, okay, if we're talking about ADS2, it looks like conformal quantum mechanics. What are examples of conformal quantum mechanics that we know about? And one that people would frequently talk about is something called DAF for these guys. And all that is quantum mechanics, just a point particle in a 1 over r squared potential. That's scale invariant and has some SL2 symmetry, as you would anticipate in formal invariance. And you might wonder, is that some prototype for ADS2? Well, I think by the time that, say, 2014 came around, there was a sharp, just purely boundary quantum mechanical description of the state of affairs. Namely, that there was a conflict between conformal word identities and non-trivial dynamics in the infrared. So if you take, ADS CFT seriously, you would have a boundary stress tensor, you would have conformal word identities. So there'd be a trace word identity that would relate the trace of the stress tensor to sources J for operators O of conformal dimension delta that would take this form. You would have a stress tensor conservation identity that would relate the divergence of the stress tensor, blah, 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 blah. And then you might also have, 2-point functions of O that exhibit scaling. And these things can't all be true at the same time. That's the statement. At least in 0 plus 1, because in that case, the trace of the stress tensor has exactly one component, the energy. And what this would be saying, essentially, is that away from the location of sources, energy is 0. Your spectrum of the Hamiltonian is trivial. You just have a bunch of states at 0 energy. And that's inconsistent with any dynamics. The only Green's function that's consistent with exact conformal invariance is something of dimension 0. Incidentally, at some point people realized too at the time that DAF was not a good model after all because it's actually not Weyl invariant, so it doesn't respect the conformal word identities despite having an SL2 symmetry. Now, this sort of problem posed this way suggests that conformal symmetry should not be exact in a good model of ADS2. It should be approximate. And with that in mind, Ahmed and Joe essentially solved this problem in gravity in a lovely paper that appeared on arXiv in 2014, finally got published in 2015. And I think it was mostly, but maybe not entirely appreciated how good of a solution they had found at the time. And without delving into the details in gravity, what they do, I can say what they did in field theory terms. What they did was to incorporate the leading deviation from conformality. So the leading irrelevant contribution to the stress tensor that's implied in holographic context when you glue ADS2 to the outside world. There's some kind of universal contribution to the stress tensor trace that appears, some leading operator, it's universal, and that thing now can account for dynamics. The other part that they needed was that, you might think that you could consistently study ADS2 at 0 temperature in the presence of fluctuations, but that's not quite true thanks to the stress tensor word identity. Any little bit of energy that you throw in, any pulse, no matter how small, carries energy with it, and it'll back react and it'll generate a horizon. Having a stress tensor that's not 0 allows you to soak that up and to accommodate that process. And so you can summarize all this through an equation of state that has not just an extremal term that would be consistent with exact conformal symmetry, but some leading low temperature correction. And the sort of moral that summarizes all of it is that we shouldn't be thinking about ADS2 in the first place. We should be thinking about nearly ADS2, things that flow to ADS2 where we keep the leading part of the flow. Now, at that time, so I told this bit about how I was working with Chris to co-referee this paper. I was there, I got a job at a place called San Francisco State University, and we made the long haul over here, started up assistant professorship in the beginning of the year. And at the time, there were a few questions on the mind besides, getting used to life as a junior faculty member, teaching courses, et cetera, et cetera. The first one was, well, what really about this proposal of Subir's relating spectral asymmetry to thermodynamics? And is that something that's really universal or not? Another one, after Ahmed and Joe's paper, was, if you've ever looked at their paper, it's quite complex. You might wonder if there's a way of simplifying what they do, making it more clear. There should be some universal dynamics that were going on. And the other one, of course, was that Kitaev had suggested that SYK models had something to do with gravity. And I was curious, given all the puzzles with ADS2, if one could really show if they have maximal Lyapunov growth, and more generally, if such a duality was sensible. And that all culminated in a paper that appeared in May on Archive. It means a lot to me. It was my first paper I wrote as assistant professor. It gave at least me some answers to these three questions that were on the mind. For the first one, hold on, I'll have to come back to it in a few slides. The main result of this paper was to recast, at least in the classical gravity approximation, nearly ADS2 gravity as this thing we now call boundary Schwarzian theory. And then there's also this business about the Lyapunov growth of ADS2 near horizons, which was essentially solved for reasons I'll explain already by Juan and Douglas in the paper they had about the SYK model a couple months before, or a month before, actually. Okay, so to tell you the result of that paper, I have to tell you a little bit about some of the basics of dilaton gravity in two dimensions that are a bit different than Einstein gravity. So suppose that we're interested in some higher dimensional theory of Einstein gravity, supergravity, whatever, that has eventually a flow to ADS2 times x in the near horizon. So I said, if I compactify down to 2 dimensions, something that will eventually flow to ADS2, and then some transverse space x, say, the usual way you would do this is in terms of a 2 metric and a scalar field, the work factor for the transverse space. And if my part that I remain that is more than 2-dimensional, then what this becomes is some theory of gravity coupled to a massless scalar. It's the usual story. But in 2 dimensions, this is not the case. And the reason is because when you write down the compactified theory in higher than 2 dimensions, you can do some field redefinition that undoes the coupling of phi to the lower dimensional scalar curvature. You can't do that definition in 2 dimensions because, at least for constant rescalings of the 2 metric, the Einstein-Hilbert term, the coupling to curvature, is Violin invariant. In other words, you can't remove a coupling of the scalar phi to the 2 metric. And so you get a qualitatively different sort of theory. And for the most general 2 derivative theory that, of these 2 fields, you can use other redefinitions to put the action in 2 dimensions into this form right here, where you have a coupling of something that's a reparametrized version of that to the 2-dimensional curvature, and a function of that scalar that you could call a dilaton potential. Now, if you look for ADS2 solutions to such a theory, you find that they exist at roots of the potential, provided that the derivative of the potential at that point is negative. And the derivative sets the radius of the ADS2 at that point. And so you get, the more, if you were to write the metric in sort of Lorentzian, Eddington, Finkelstein coordinates, it would look like this for some function sigma of t here that I'll talk about in a moment. And then, well, this is, if you studied the finite temperature version of this, there would be an entropy that's just extremal. It's independent of all parameters. It's just a constant. Depends on the dilaton at that point. This function here is a free parameter of the solution. All these metrics are r equals 2. And you can think about that sigma of t as the statement I was making earlier about infinite dimensional conformal symmetry. Start with the ADS2, act with a conformal transformation on it, it hands you another solution to the Einstein's equations. Right, so what you get at this point, this is our ADS2 that we were looking for. This is something like a conformal quantum mechanics. And if you compute holographically, the energy on the boundary, the stress tensor, you're getting identically 0. Of course, that's not what we want. We want to incorporate the leading deviation from conformality. And a natural way to do that would be just to look at, let the dilaton explore a little bit of the potential away from the root. Alternatively, you could just start building up perturbative solutions to the equations of motion here, where you start to explore the potential. I should have mentioned this sigma of t here. This thing is this curly bracket. This is something called Schwarzian derivative, defined, which is familiar from the study of projective invariance. Okay, so how do you go from there? Well, natural thing to do is to shift the dilaton by a constant so that we don't have this annoying phi minus phi naught, and it's some linear behavior of u away from its root anymore, and also to work in units where the radius of radius 2 is 1. And then the effective description that you land on is, well, there's the constant piece in the dilaton times the curvature. That's a topological term here, and if you compute the coefficient, it's S naught over 4 pi, and so it's S naught times an Euler term. And then there's this thing phi times r plus 2. And I've written all this up to boundary terms. And now we recognize this. This is this thing called Jaquet-Titaboyne gravity, which now we have seen hundreds of papers about and heard hundreds of talks about. At the time, it took a reminder that Jaquet and Titaboyne had written down this theory back in the early 80s, before I was born. Now, if you ask in this model, so not in the one before, but in this model, what are the classical trajectories? What are the classical solutions? Well, if you look at this, phi is acting as a Lagrange multiplier, enforcing that the curvature is constant. And then you have to solve for the dilaton as well. And so the solutions that you get, they're of this sort, where the metric looks like a two-dimensional black hole, and also where the dilaton has some linear growth near infinity, near its boundary. And if you go ahead and, well, if you look at this for a moment, you say, oh, well, there's my conformal symmetry breaking. I introduce a scale into the problem. The dilaton is blowing up like R. That's the leading deviation now from conformality, is this behavior of the dilaton, even though the metric is just plain old ADS2. And if you go ahead and compute, the black hole thermodynamics here from, the Euclidean continuation, you would see that RH is the temperature, and then there's some free energy, which has an extremal part, and then a correction encoded by the growth of the dilaton, and with it, a reservoir of energy that can soak up whatever pulses you chuck in. Now, this is pretty boring on its own. This is just a, equilibrium state. What are the dynamics? Are there any excitations? Are there any modes that we can keep track of? And at least for me, what was on my mind was what Joe and Ahmed had done the year previously when they studied their version of this problem, which was to send in some matter. Because in the absence of sending in some matter, you're studying a system where, your energy is just conserved. There's no stress tensor dynamics that remain. So what else can there be? So something very basic that you can do is just to couple a minimally coupled massless scalar field chi to the problem and send in some pulse of it from the boundary. That amounts to solving the problem of the effective stress tensor that you get from this is like that of some null incoming dust. And, well, it's very easy to solve in enclosed form what the metric and the dilaton and the scalar chi, what their form is. And so I'll rewrite the ADS2 in its most general form in terms of some function sigma of t here. There's the dilaton growth. The scalar is particularly easy to solve in this case. And that's most of the Einstein's equations, but there's one that's left, and it can be recast as a purely boundary equation. What it does is it relates the energy that you would get on the boundary, which in this case you can use the holographic dictionary to figure out what it is in terms of this variable sigma of t. It's the Schwarzian derivative of that reparameterization sigma. And the remaining Einstein equation that's left is nothing more than the boundary ward identities per stress tensor conservation, saying that the derivative of the energy goes like the derivative of the source that you turn on times the expectation value of the dual operator. Okay, so that's how you could get some dynamics. You send in a pulse, energy responds. And the miraculous thing is that that equation of motion could be written down as purely this is unlike what happens in higher dimensional gravity. You could write it down as the variation of a purely 0 plus 1 dimensional action, now known as the Schwarzian theory, where that action, okay, well, I guess it would be a logical term, so there'd be exactly one part that's higher dimensional. But then you'd have a part on the boundary, that's the Schwarzian derivative of the reparameterization, and then a piece that accounts for the matter that you're throwing in. This is the Schwarzian theory. And the nice thing about it is that, well, now we see that this degree of freedom, sigma that I wrote down, this is an honest-to-God degree of freedom of the model. It's a fundamental field. Presumably, in the quantum theory, you should integrate over it, although that wasn't clear from the derivation that I just gave. And then also you can see how it would couple to quantum field theory, to matter degrees of freedom, classical matter degrees of freedom when you started sending them in. So that argument I presented above, it's the one it's essentially the argument that's presented in my original paper. And the way of thinking about it is that there's a large diffeomorphism degree of freedom in JT gravity, and it becomes this boundary degree of freedom, the Schwarzian mode. And I think of it as a streamlined version of Almeri-Polchinski, and if you go back and you look at their paper, you'll see why I say that. Now, this description that I gave, it's not really a complete description of the say, a two-sided black hole, the one at finite temperature, because, well, if you study, here I'm working on sort of, one boundary and sending stuff into a horizon, so it's something that would compute the gravitational dressing of retarded functions. But if you're interested in all the Whiteman functions and the problem more generally, you better account for the fact that, well, there's this, you have a thermal field double, there's a second boundary, and then there's some moduli that glue everything together if you do it really properly. The derivation that I gave, it's complementary to that of Juan and Douglas and Zhenbin, where what they did, they considered the Euclidean cigar, the hyperbolic disk, and they were able to rewrite JT gravity in that setting as a single boundary theory, often described as that of a wiggly boundary, effectively of a large diffeomorphism mode. And the nice thing about their derivation, because Zhenbin's not talking about it, so I'll say some things about it for a moment, is that you can ask really what's the field range of this variable? How are you integrating over it? And they make it very, very clear. There's a reparameterization. I'm writing it as a reparameterization of tau being Euclidean time going around the circle with periodicity beta. This variable is a funny one. It's not an unconstrained field. It's something that lives in a coset. It's a reparameterization in the circle subject to some SL2 gauge redundancy, which you can think of as being inherited from the SL2 isometries of the ADS2 background, which are broken by the presence of the dilaton. And the nice thing about this description, of course, is that you can use it for computations. If you were to study correlation functions of boundary operators, well, those now talk to this reparameterization mode, and that leads to exchanges of the reparameterization mode, which dress correlation functions in a very computable way. Okay, so one of the other things that I had on my mind when I wrote this paper long ago was this connection with SYK. And at the time, I was quite a bit of a contrarian about the idea that SYK was exactly dual to ADS gravity. And maybe it's worth pointing out what the thing was that bugged me at the time. The thing is that in SYK, not only is it a disordered theory, somehow that didn't bother me as much at the time. The thing that was irritating is that in SYK, you have a huge global symmetry of the just averaged correlation functions. It's an SON symmetry. And I didn't really see what this could have to do with gravity. Because it's a symmetry on average, there's no conserved charge. And this leads to certain problems. So for instance, you could say, okay, well, maybe the fermions of SYK have some gravity dual in terms of fermions in the bulk. That's problematic because you would have n of them, and the effective scaling of entropy in G Newton would be of order 1 over n. That leads to problems. You don't have semi-classical gravitational theories when the number of bulk degrees of freedom is comparable to the inverse G Newton. Alternatively, you might say, a la what one does in the context of vector models, Chern-Simons matter theories, maybe gauge this symmetry, but because this is only a symmetry on average, you can't do that for SYK. Something you could try to do is to say, well, maybe just the singlets of SYK have some gravity dual, and I think this is essentially what some people had in mind. And you could ask if there was an effective field theory in the bulk that would reproduce those correlations. This was a line of reasoning that was pursued by Vladimir Rosenhaus and David Gross to great effect. And you get something. You can kind of reverse engineer a bulk theory, and doesn't look entirely local, but okay, you can push on it. The thing, though, that became clear to me after these 2016 papers was that the real connection between SYK and JT gravity wasn't so much that there's some detailed duality with the SYK model, as much as the fact that both of these things, gravity with some ADS2 near horizon and the SYK model, they had some common low energy description, this Schwarzian theory. In other words, you can think of both of these things as being akin to two different superfluids that would have the same Goldstone description, at least up to parameters in the infrared. And the maximal Lyapunov growth that Kitaev found in the SYK models, well, this, it turns out, is actually a consequence of this Schwarzian description and no other dynamics. So it had to be the case that SYK had this once you knew that it had a Schwarzian description. There was another thing that was on the mind at the time, which is that so I mentioned earlier that the equation of motion of the Schwarzian theory was the stress tensor conservation, E dot is. And that rang a bell because, a lot of my time as a postdoc, I had spent it thinking about hydrodynamics in modern language as an effective field theory of many body states. And at that time, theorists had been developing an effective field theory treatment of both dissipationless and dissipative hydrodynamics, which culminated in a series of papers by Felix Heil, Laganayagam, Mukund, as well as Crossley, Glorioso, and Wu. And at least in the non-dissipative versions, the effective field theory, it's a kind of sigma model. And the important thing about it is that its equations of motion on the nose are in these stress tensor conservation and current conservation. Turns out that the Schwarzian theory you can write as on the nose as such a dissipationless hydrodynamic effective theory. That was kind of nice. It was nice as a mental model because the Schwarzian theory, like hydrodynamics, is giving you an effective description of a system with a huge entropy, with many microstates, without actually being a theory of the individual microstates. If you were to quantize it, it has fluctuations that contribute an order 1 amount to entropy, not order 1 over G Newton in this case, just like that of hydrodynamic modes. Now, of course, the modes of the Schwarzian theory, they encode some physics. I already mentioned that they are responsible for the maximal Lyapunov growth. That was another nice result that was demonstrated by Juan and Douglas, and also by Zhenben in the context of JT, that they lead to a loop-corrected equation of state. This is the classical contribution. And then there's a quantum mechanical one at one loop coming from the Schwarzian modes, a T log T. And then later this was shown remarkably to be an exact result in JT gravity, not just a one-loop approximation. This logarithmic correction, of course, dominates at sufficiently low temperatures over the rest, and that effect is the beating heart of recent work, starting with Luca Iliescu and Joaquin Turiachi, and along with many later developments, showing how the statistical mechanics of low-temperature black holes is modified by large quantum corrections at low temperature. This is the central observation. Yeah.
zero, but it's still like that.
I think maybe you may have in mind some repackaging of some shuffling around of things here. I'm just saying you have a 0 plus 1 dimensional degree of freedom, effectively with 3 modes removed. That's corresponding to the 3 here. That's completely independent of G Newton, that 3. Well, no, the effect of the whole Schwartzian mode on the thermodynamics, on the one loop determinant that computes the partition sum, the thermal partition sum of the model. That is, I'm saying that is this right here. That's right. I'm talking exactly. Okay. That's the. Yes. This will be the analog in higher dimensions of computing the determinant that comes from, say, the viscous mode of an ADS black brane. This would be the analogous contribution. Okay. Right. So I talked about this reformulation of Almeri-Polchinski, maximal Lyapunov growth in SYK models. I should come back to this thing of Souvir's. So at the end of 2016, I had the privilege of getting to write a paper with Souvir and many other lovely people talking about what you would now call charged SYK and its connection with a low-energy Schwartzian theory that is able to describe the presence of an extra global symmetry, chain versions that were popular at the time to discuss transport. And there's an appendix in there, Appendix B to be precise, which demonstrates that this relation I mentioned long ago actually is a consequence of low energy conformal symmetry after all, and thus independent of the dynamics. Other than that the dynamics needs to produce the low energy conformal symmetry in the first place. Okay, so that's what I wanted to say about JT. Maybe I'll go on to talk a little bit more about 3D gravity, what kind of work this led into. So since 2016, of course, there's been an enormous amount of activity devoted to JT, including by many of the people in this room. Too many papers to talk about, although I'll mention a couple shortly. But to take a step back, long before JT, the kind of workhorse for simple models, what we thought were toy models of quantum gravity at the time, was not JT, but rather 3D gravity. So, 3D gravity with negative cosmological constant. So something that Alex Maloney had been working on for years, for example. Now, classically, 3D gravity with cosmological constant, it's equivalent to some Chern-Simons theory, at least in perturbation theory. And that description makes it clear that a fact that you kind of already know from other means, that there's no propagating gravitons in 3 dimensions. There's just boundary ones. After JT, this was on my mind a lot, because in JT, you also don't have bulk gravitons, you have boundary gravitons. That's effectively the Schwartzian mode. There was also a fun fact about 3D gravity that reminded me, it seemed like it should be similar to the story with the Schwartzian, which is that, so recall that in higher dimensional ADS, we can find hydrodynamics by solving the Einstein's equations perturbatively around some black brane. This is the fluid gravity correspondence. And in ADS3, that correspondence, it's an exact property. The fluid gravity expansion, if you do it in the right variables, it truncates at order derivative squared. So there's some exact rewriting of the dynamics of excitations of BTZ in terms of a hydrodynamic description, a dissipationless one. And these facts convinced me that there should be some higher dimensional version of the Schwartzian theory. But I didn't know how to do it. And in late 2016, there was a young PhD student at Stanford, Jordan Kotler, who very enthusiastically came to me and said that this sounded like a great problem and he wanted to work on it with me. So we started working together and eventually ended up co-supervising his PhD. And it took us a long time and an enormous amount of confusion and some help from Herman Berlinde, but eventually we figured it out. And it resulted in a paper that appeared in 2018. And let me talk briefly about the idea behind this. So why there's a higher dimensional version of Schwarzian and what is it? So here's 3D gravity with negative cosmological constant. It has a dimensionless parameter in these units because I've set the ADS radius to 1, which is g Newton, which I take to be very, very small, or equivalently, the central charge, 3 by 2 g Newton, to be very large. The basic solution to the equation's motion of this model is global anti-de Sitter space. It was just the solid cylinder with that metric. And unlike in JT gravity, now there's dynamical excitations. There's boundary gravitons. They're non-trivial states in the Hilbert space of this theory, and they swirl around the boundary at the speed of light. The classical version of this model is exactly soluble. It's probably not surprising since it's essentially Chern-Simons theory. And the phase space, often called the Bagnados phase space, is also spelled out by Maloney-Witten in their seminal paper. It's 2 copies of the same quotient that we encountered earlier in the context of the field range of the Schwarzian model. The phase space can be quantized. This is what Maloney and Witten do in their paper, leading to a Hilbert space that's 2 copies of the vacuum representation of Virasoro. And, well, then if you go ahead and interpret the path integral, say in imaginary time and compactifying it as computing a trace over this Hilbert space, you get an answer for the torus partition function that you would get from continuing this to imaginary time. That's just the vacuum character of Virasoro at the central charge C. And in Maloney-Witten, what they did was to say, well, if that's the contribution from the thermal ADS, that can't be the only contribution. There has to be modular images, because in thermal ADS, one of the boundary cycles of the torus pinches off, and we should sum over all possible ways it can contract. Could we get this from an analog of the Schwarzian? That was kind of the question that we were asking. And of course, when you pose a question like that in talk, the answer is yes. And so how do we do it? So what we did was the following. So we studied 3D gravity in the first order formalism, so in terms of dry-bind and spin connection. And formally, gravity resembles, as I mentioned, some non-compact Chern-Simons in that case. So you can form a field A and A bar out of E plus and minus omega plus and minus E rather. And well, then you can try to perform a path integral quantization of that. The more modern version of this is what Lorentz and friends have developed, now known as Virasoro TQFT. So the idea from a Chern-Simons point of view is you separate out a time direction from the rest. And when you do that, the time component of your field acts as a Lagrange multiplier, enforcing a constraint, just a spatial flatness constraint. You solve that constraint, you get a residual theory of the moduli space of solutions that satisfy the constraint. And in 3D gravity, it's important that there's also a boundary term that gives you an effective energy function on that constraint space. And the end result that you get from this is a theory of 2 fields, 2 degrees of freedom, call them phi and phi bar, although they're maybe those bad names, but they're both real. We had to give them different names. At fixed time, these things are funny. They're the elements of this quotient space that appeared earlier in the context of the Schwarzian theory. And you get some action that's the sum of a contribution from just phi and some other contribution from phi bar. And you should think of these as the left and right moving boundary gravitons, respectively. You get some action for them that's nonlinear, and if you stare at it for a bit, you realize it resembles the Schwarzian theory. And okay. This model had actually appeared previously in the literature. It was a classical Lagrangian that was written down in a paper of Anton Alexeyev and Samson Shadishvili in 1989, when Alexeyev was an undergraduate student in Moscow. And well, 1989, you know what happened at that point. So their collaboration together ended shortly after this. And from their point of view, this action appears because this space that I keep talking about, diff S1 mod SL2, it's not just any old quotient space. It's a very special kind. It's a symplectic manifold. And it's something that's called a coadjoint orbit of the Virasoro group. Well, it's not just any old symplectic space, it's a very special one. It's endowed with a nice action under Virasoro. And what the classical Lagrangian describes is motion on this space. And what this structure means, if you take the motion on a coadjoint orbit and you quantize that thing, what it produces, it's a nice piece of mathematical physics. It produces a Hilbert space, which is a single irreducible representation of the underlying group whose orbit you're talking about, so in this case, Virasoro. And the path integral with imaginary time formalism is computing a trace or a character of that representation. Given what I said earlier about the vacuum representation in ADS3, now it should be clear what's going on. The representation that you get, the quantization of this orbit, is giving you the vacuum representation of Virasoro, and the Euclidean path integral is just giving the vacuum character. Here we're able to demonstrate that just completely using path integral methods. The sort of torus partition function of this model is in fact one loop exact. It's computable and gives you this vacuum character on the nose. And then the Maloney-Witten result just follows from an extra step where we sum over all possible ways of contracting a boundary cycle. So we succeeded. We're very happy about this. Of course, we get more than that. If I think about it in terms of operator-state correspondence for a moment, in the vacuum representation of Virasoro, the only local operator really is the stress tensor plus its Virasoro descendants. And so there's no real interesting local operators in this theory to study, but there are non-local ones. There's bilocal operators that one can write down that are very analogous to the bilocal operators of the Schwarzian theory that encode the coupling between the Schwarzian mode and matter. And if you compute correlation functions of these bilocal operators, what we showed at the time was this is encoding semi-classical Virasoro blocks at large central charge. And so you take one of these bilocals, another one, modes of these phi fields and phi bar fields are exchanged, and that encodes in CFT terms stress tensor exchange and so on. And if you compute this out, you find that you're able to reproduce all the usual light, heavy, light, hefty kind of limits that were known at the time for Virasoro identity blocks. And you can even get the maximal Lyapunov growth found by Dan Roberts and Douglas Stanford a couple years before. So it's useful. This diagram, this funny analog of Schwarzian, it gives you the Virasoro blocks to boot. Try to have like 6 minutes. Yeah, I think I can do it in 6 minutes. Okay, so that was a great success. There's one more paper I want to tell you about, and then I'll end. The next year saw the seminal paper of Saad Schenker Stanford. Many things to be said about it. You all probably know many of them. The two things that were important for this next project I'm going to describe was that, one, this was extremely surprising to me at the time, is that JT gravity, for all practical purposes, is a consistent theory of quantum gravity on its own, without including any additional degrees of freedom, any other strings and whatnot. That was very surprising. You can consider JT gravity on any topology Riemann surface, and its ultraviolet behavior is finite. Of course, there's the question of, then the sum over topologies and so on, but at least at the level of individual topologies, it was a consistent, well-defined theory of gravity. The other thing was that its genus expansion is not just finite, but computable. And it's equivalent to that of some formal matrix integral with some leading density of states, sinh square root, and where all the corrections are determined by topological recursion. And along the way, in order to demonstrate this, Saad Schenker Stanford developed a dictionary between moments of this random matrix, call it H, Hermitian matrix H, and the double scaled limit, traces of e to the minus beta H were dual, what they found, to asymptotically nearly Euclidean ADS boundaries where the circle has some renormalized size beta. In particular, the leading sort of, they considered not just the one boundary problem that would compute the average trace e to the minus beta H in this ensemble, but moments of trace e to the minus beta h. The leading contribution, for instance, that they would get some wormhole that would connect multiple boundaries. Well, this, they showed, encoded real, honest-to-God physics. This wasn't just something that was an redheaded stepchild, something that you wouldn't want in your life. It was something that was really important. It encoded some physics that you should have anticipated if you were thinking carefully about black hole microstates. Namely, encoded long-range level repulsion, or equivalently a ramp in spectral form factor. So you consider trace e to the minus beta h, trace e to the minus beta h, and then continue the two betas. The connected part of that average behaves like the time t at large but not asymptotically large time. And that behavior, that corresponds to, that's something that's predicted from random matrix universality. Here is maybe not so surprising because you're actually equivalent to a random matrix theory. And okay, that was very nice. So a question that Jordan and I asked at the time was whether or not we could uncover, or with all this in mind, should we revisit the status of 3D gravity? So I told you earlier about the Maloney-Witten partition function. This was written down in 2007. Why weren't people thinking of 3D gravity as a consistent theory of gravity? Well, the Maloney-Witten partition sum has problems. It's a sum over modular images. That sum diverges. And so you try to regularize it. Natural thing to do is to regularize it in a modular invariant way. And when you do that, you no longer have an answer that has a positive definite density of states. The density of states is continuous, and in fact, it's negative, very close to the spectral edge at high spin. That was a problem. You would say, okay, 3D gravity is not a consistent theory of gravity after all. That was the conclusion of Maloney and Witten at the time. But then, okay, after Sodchenko Stanford, you might ask, well, maybe 3D gravity is consistent after all, but not just as a single CFT, but as a statistical distribution of, well, maybe CFTs, maybe CFT data, maybe approximate CFTs. I think it's still a subject of some ongoing research to nail down exactly what that would be, as well as whether or not 3D gravity is consistent after all. At the time, a simple question was maybe the sum over topologies cures the negativities in the Maloney-Witten density of states and encodes some other physics besides. And sometimes things go slowly and sometimes they happen all at once. Within three weeks or so, there were 3 papers on arXiv in the month of June, so it's contributed to the madness of summer 2020, that gave significant progress toward these questions. It's a paper of Alex Blin and Jan de Boer, where they took known solutions of 3D gravity, where they're describing wormholes, where you have a genus 2 surface on one boundary and a genus 2 surface on the other, and they were able to show that that was consistent with a statistical distribution of OPE coefficients in a purported dual. That would be consistent with randomness. We had a paper, the one that I'm getting to, where we computed the 3D gravity version of the double trumpet, which in this case ends up encoding long-range level repulsion for BTZ microstates in a way that is consistent with random matrix universality, upgraded to account for the symmetries of a CFT. And then just after us, Henry Maxfield and Joaquin Turiachi exploited a JT limit of 3D gravity to sum up a whole bunch of contributions to the one boundary problem, so the thing that would compute the average torus partition function. And their results appear to cure the negativity of Maloney-Witten. And all taken together, these things comprise excellent evidence at the time for some statistical interpretation of 3D. Just thinking a little bit, so I want to respect the time. So I could give a whole talk about our computation, the one of this double trumpet. It's a fully off-shell computation in 3D gravity. There's a theorem, the Witten-Yau theorem, that shows that the thing that we considered was the problem, the 2-boundary problem, where both boundaries are tori and they're just connected in the obvious way. There's no hyperbolic 3 metric on such a space, so there's no saddle point approximation. And in order to perform this computation, to compute this amplitude, we really just had to roll up the sleeves and sum up all metrics. And I could give a whole talk about that, and I can't because of various constraints. I'll just flash that there's some answer that I'm particularly fond of, and where Cynthia Yan also pointed out we were off by a factor of 2. What this answer encodes is the same physics of a ramp in spectral form factor that I mentioned previously, but to see it, you have to do a little bit of work. In 2D CFT, you have many degeneracies in the spectrum of states on a circle that are implied by the Virasoro symmetry, and in order to look at spectral statistics, you need to kind of mod out by those degeneracies. So the thing to do is to consider the correlations of primary states of fixed spin. That's the thing to do. And when you do that, you find ramp statistics in each spin sector with the correct coefficient that you would predict from the right ensemble, exhibiting symmetries of the problem. Now, more recently, there's been some very impressive work continuing this story. And I should say it's an ongoing story. I think it's one that more people need to contribute to. There are many on-shell configurations of 3D gravity that involve wormholes. For instance, the genus 2 wormholes that I mentioned previously that Jan and Alex studied. So Scott Collier, Lorenz Eberhard, Menglin Zhang, they were able to efficiently recast the computation of 3D gravity amplitudes on such manifolds as a sort of TQFT that they dubbed Virasoro TQFT. Relatedly, Jeevan Chandra, Tom Hartman, Alex Maloney, and friends, they were able to make some progress in building up the statistical distribution of OPE coefficients implied by these wormholes in CFT terms. And you might think at that point, oh, gravity is some distribution of OPE coefficients, maybe it's secretly some TQFT, but that's actually not the case. Some contributions to 3D gravity can be described by TQFT, but not all. For instance, this torus wormhole, oh, I went the wrong way. This torus wormhole that I was describing, the TQFT of Scott and Lorenz and friends predicts this thing to diverge, to be infinity. And the reason why it's not in 3D gravity is because this manifold has a non-trivial mapping class group, and that leads to the answer that we find. So the gravitational path integral is sometimes equivalent to a TQFT here, but not always. And recently, there was a lovely paper last summer by Dan Jafferis and friends arguing that, well, maybe 3D gravity is dual not just to a distribution of OPE coefficients, but also something that involves a matrix degree of freedom as well, and where there's, I think, a lot of work should be done to try to compute things that could, on that would be matched to 3D gravity amplitudes, and concurrently to match corresponding amplitudes in 3D gravity. This is my last slide. Promise. There's thank you is on the next slide. So, taking a step back from all of this, I am sort of shocked that we're still, if I went back in time and told myself at the end of 2016 that we're still all thinking about JT gravity, I would have been absolutely shocked. I thought at the time that the story was more or less closed by the end of 2016. And the reason why was because of traditional logic in quantum field theory. What happens in quantum field theory usually? You have some UV degrees of freedom, they get coarse-grained to the IR, and that IR theory is very nice, but it has its limitations. It has its regime of validity. In this case, the Schwartzian theory was what I was thinking of as the IR theory. And on those grounds, okay, you explore phenomena, the analog of pion scattering and such, and eventually you move on. History was much more interesting than I had certainly anticipated, and I was racking my brain planning this talk, thinking if there's a quantum field theory analog of this effect, and I'm really unaware of one. JT and its variants, maybe even 3D gravity as well, they're behaving like on their own, like UV complete models in their own right. And they're not quite theories of the microscopic degrees of freedom that build up space-time, they're almost. Those, I guess, would be the matrices and the matrix tensor, if that's really the case in 3 dimensions. But they're working really well, far more unreasonably effective than I would have expected at the time. And Jordan has, in our conversations, he's dubbed this phenomenon with borrowing some of the language familiar from quantum chaos, that maybe we should think of these low-dimensional theories of gravity as mesoscopic theories. something intermediate between the UV, between the IR. They're not truly degrees of freedom of space. They're not incorporating the matrix eigenvalues that build up space-time, but they're coming pretty close. And with that, I will say thank you very much for your attention. Yeah.
SYK. So what is still the advantage, if any, of SYK over JT? If JT, you said, is basically a UV complete theory of quantum gravity?
I mean, so JT has a lot more in it. So JT has a number of very interesting features in its own right. A model doesn't have to be holographic for it to be interesting, right? So JT has many more states, it has many more operators, it exhibits much richer phenomena than we get in perturbative gravity or even including genus corrections. So for instance, just to give an example of this, one virtue of SYK is that it allows us, when you study it, you can go away from the limit of maximal chaos. So in gravity, if you want to go away from maximal chaos, you have to do some pretty violent things. You need to incorporate stringy corrections and things that we don't really understand in detail. We don't have a good effective description of those. In SYK, it just hands it to you. For instance, in the vanilla SYK, once you go away from very low temperature, and more generically in so-called double-scaled SYK. There's other things that the double-scaled SYK might be good for as well that people have been investigating a lot. There's some claims that might be related to de Sitter physics. But I would stress it doesn't have to necessarily even be holographic for it to be interesting as a model of solvable strong coupling dynamics. That's right.
So is the difference that the representations in the Hilbert space and dimensions, representations of KSL2R, cross KSL2R, because in JT it's actually this representation.
Yeah, so that's part of the difference. The other one is that, roughly speaking, the 3D theory is the quantization of the phase space, whereas if I think about the Schwartzian path integral, I'm just ripping off Douglas and Edward here, you should think of the Schwartzian path integral as the statistical mechanical partition sum. It's an integral over this space, diff S1 mod SL2. It's an integral over a phase space, weighted by some e to the minus beta h effectively. Whereas in the 3D gravity case, you're taking that space and you're quantizing it. You're looking at motion on the phase space and summing over the histories on it, closed loops. Yeah. That's right. So I'm just adopting the kind of not what you did with Alexei here. I'm just talking about the Okay. Maybe the representation theory. Yeah, here it's important that in the 3D story, you just get the vacuum representation when you quantize. You don't get anything else.
What's the difference between Virasovati QFT and Alexei
Shadashvili. Yeah. And Jensen.
Difference?
So the case that I was flashing, so this Alexei of Shadashvili is the analog of Schwartzian in ADS3. And so when we wrote this paper, we didn't, this was before Lorentz. So we had no idea. We were just kind of doing things in a very mechanical way. You take the field ranges that are given to you by gravity, by solving the constraints, and you make sure you pay careful attention to global considerations, and this is what you get. They get, in their TQFT, it reorganizes these kinds of computations significantly. They get, for instance, just this vacuum character as a simple output. If they were to consider the same disk time circle that we consider. Probably if they dug into it, they can see this Alexei of Shadashvili theory as well, but there's it's a little tricky to describe. Their thing, it reorganizes the computation so that you don't really have this intermediate description in terms of boundary modes.